So find the functionality. So the question here is find the functionality of this circuit, right? So here I have given you six uh, transistors. Among them, there are three PMOS and three NMOS, and there are two inputs A and B, right? So you have to find what the function the circuit is implementing, and the output is taken from the point in between this point. So this type of questions, there are two ways of doing. You can see what are these individual circuit blocks instead of seeing the individual transistors. Like you can name, for example, one option is you can name the individual transistors. For example, you can name this as P1. This transistor is P1. Maybe size. What is the size? Okay. So this transistor is PMOS one. This is PMOS two. This is PMOS three, and we have NMOS also. So I'll name it as this is NMOS one. This is NMOS two, and this is NMOS three. Okay. So one way of analyzing is look at the individual transistors and see whether they are on or off. Right? If you see all those six transistors with respect to A and B, whether they are on or off, you know what is output. Definitely, you will get the logical value of out. Right? Another option is you see the block level. You see top level. This is an inverter. You can see this is an not gate or inverter. Right? So the input is A. So the output is A bar. Now you're looking as a block level, the top level, the inverter. Now we can see there's another kind of inverter kind of structure here. Input is B, but the difference is in the inverter it is directly connected to VDD like in the left portion, but here it is connected to A. You can see A is going instead of power A, and bottom you can see A bar. A bar is supplying the bottom of the bottom supply to the inverter. You can see that difference, right? Right. So a inverter with the VDD or the power as A and ground as A bar, right? So that is the thing. And this part is simple a PMOS and NMOS connected in parallel, right? So we can see one point input is going is one point input to is A, and there is A bar. A bar is going in the bottom, right? So this the way what I'm discussing is in order to find the functionality of any circuit, you can analyze in different ways. One way is you are seeing the pattern, like there's inverter, there's another inverter, there is two, and there is you just analyze the individual transistor owning and offing based on A and B and find out logical value of output. That is also fine. Whichever value, whichever way you are fine, you can go ahead with that. But as you go on practicing, as you see a lot of circuits, you can easily find the pattern like this is inverter and all those. They're much easier and much faster. So let's start with the first way of doing things. The first way is let's assume A is give A some value. For example, so here let me give initial value of A to be 0 and B also should be 0 for assuming 0 0. What happens if A is 0 and B is 0? Right? So we know A is going to the input of this inverter. So A bar, that is 1. 1 is coming into the A bar. So 1 is coming in this bus. Okay, 1. This is 1. Right? So but A is going. Right? Now the B is going. Now B is going here, and B0 means this PMOS is on. PMOS is on. This PMOS is on. This PMOS is on. And NMOS is off because input is gate 0. Right? PMOS is on. So A is coming here at this point. You can see A is coming here, and the output is just getting value A. Okay. So we got the output A. So if you analyze this way also, the B is also going. 0 is also going here. And what about this PMOS P2? A0 PMOS is on, right? PMOS is on. You can see PMOS is on. So this PMOS is on. So B0 is going also. And this N2 is also on because A is 1. So this is also on. So 0 is also going to A. So A equal to 0 and A equal to 0. Output is nothing but 0. Okay, so I'll just analyze once again so that we can see once again why. So here we are assuming A is 0 and B is 0. Okay, so this is a inverter, input 0, output is high, right? So this high value is also coming to all these nodes. This one, this is all node is 1, and this 0 is also going to the top of this point. Okay, now B is also going to this point. B is also going here, nothing but 0. Okay, now B, this PMOS is on. That means this PMOS is on means this node is getting a value 0. And this NMOS is on. This NMOS is also on. This PMOS also. So 0 is directly going from here. Both sides 0 is coming and output is nothing but 0. Okay, the DC, right? We're just giving some value to A and B and seeing which all transistor are on and just seeing what is signal at the output. So here when A is 0, B is 0, out is also 0. Okay, first condition A, B, out, O, out. Okay, so 0, 0, 0. Now let's give some other value. Let's give a value of now let me make 1 bit high. So here if I make A, the value of A instead of 0, if I make 1, what will happen? Now this is 1 and output is here is 0. So 0 is coming to all these initial ones. Okay, all these are zeros, right? So this NMOS is also off, and now B, now this one is also going through this PMOS to this node. So this also become 1. This also become 1, right? And this B is also 0. B is also 0. And the B is also coming through here, and here 0 is coming. But here NMOS is off, PMOS is also off because this is 1 in one input gate. So this is off. So here my output 0 changes to 1. When A is 1, B is 0, output is 1. Okay, right? Now let's change the value of B here. Instead of 0, I change the B's value also 1. So what happened? Now this is going here, 1 is coming here also, right? And this B is high means this PMOS is now off now. NMOS is on. This NMOS is on, right? So now the A on the bottom 0 is coming and coming to the 0. Now 0 is coming to the picture in the output block, right? At the same time, B is also 1. That means B is coming from here, waiting here. But the bottom NMOS is off, PMOS is also off because this is also 1. A is also given 1, right? So here the output changes from 1 to 0, right? So when I make A1 and B1, the output is 0. Okay. Now let's see the last condition. When B is 1 and A is 0. When B is 1 and now we change the condition of A, A to 0, A back to 0. A is 0, then A is back to 0. Now the output of this inverter is 1, high. So this bottom is getting high, high, high. And B is 1. So this NMOS is on. So 1 is going to the output. 1 is going to the output. 1 is going to output. Again, you can see this 1 is making this NMOS also on. So B is 1. B is also coming through this way also. So now output becomes 1. That means A is 0, B is 1, output is 1. Okay. So ultimately, what was the truth table we are getting? Now we are getting a truth table like this: A, B, and out, right? So 0, 0, we got 0, 0, 1, we got 1, 1, 0, we got 1, 1, 1, we got 0. So which gate is this? Which gate is this? Which logical gate? You can type. You can type and see. which logical gate this we are discussing. Yes, no answer. Yeah, this is simple, uh, simple XOR gate. Why? The inputs are same, my output is 0. When inputs are different, my output is 1. Okay. So how I analyze the circuit? I analyze transistor wise. Individually analyze the transistors, and I'll see what is 1, what is 0, like that. Okay. So this way I analyze the circuit and got this XOR gate. So in this, there are two basic structures. One is this structure, inverter kind of structure, and another inverter kind of structure is also there in the input of B. There are two structures, inverter kind of structure. Another structure is like this. This is called transmission gate kind of. It's not as important for you, but you can see structure is very simple, right? And you can see in this one input to the PMOS is A, and input to the NMOS is A bar, right? So either both the NMOS and PMOS are on, or both are off, right? Because PMOS is getting A, NMOS is input is control gate is A bar, and PMOS is getting 1, NMOS is getting 0. If PMOS is getting 0, NMOS is getting 1. So both having the same state together. Okay. Although these questions are simple and you need just patience to analyze which is on, which is off, and see the short circuit and the output value. And there's one extra resistance which I have not given yesterday to you, that is just for current control resistance, right? So that is resistance put to reduce the current from the voltage source, to improve the power dissipation, to reduce the power dissipation. Okay. So so this circuit, I think this circuit has two parts. We'll discuss once more what are those parts. Okay, so let it on. By the time we can discuss one more circuit which I shared with you in the Google Classroom. So also there's some issue. This so by the time we'll discuss the other circuit. So this is another circuit which I shared with you. It looks very complicated. There are a lot of switching. I think there are around eight, yeah, around 10 transistors. So, but you can, if you see the pattern, if you see the pattern here, you can see something which we already discussed. You can see this circuit we already discussed, the right wala. You can see these two NMOSs are in parallel. These two NMOSs are in parallel. N1 and N2 are in parallel, and PMOSs are in series. P1 and P2, right? So this is some gate which we already discussed, right? Again, we can see this another circuit which we already discussed is this. This circuit is also something which we already discussed. Here two NMOS are in series, N1 and N2, and PMOS are in parallel, P1, P2, for example. And this also we have discussed. And this last circuit also we have discussed. You must know this is nothing but only a one PMOS and one NMOS, P1 and 1, right? And this is nothing but a simple NOT gate we have discussed. So if you see very carefully, you can easily see that this is nothing but an NAND gate, and this is nothing but a NOR gate. NOR gate, how I conclude? Because both NMOS are in series, sorry, parallel. In NAND gate, they are in series, right? And same time, if NMOS are in series, PMOS are in parallel. And in the NOR gate, if NMOS are in parallel, PMOS are in series, right? So this is the peculiarity of NAND gate and NOR gate in CMOS implementation. And this is my NOT gate. Last gate is NOT gate. So we can easily understand what does this gate indicate, all these circuits indicate in a top level view instead of going transistor level understanding, right? So how we analyze this? So initially we see that, yeah, this A and this output of this NAND gate will be A into B dot A into B bar, all bar. This is the, right, this is the output of the NAND gate, right? A and B are input, output is A into B bar, right? So, and this is going to the input of the PMOS and NMOS, right? Can see A into B bar is going to both. And what is going to the input of the second PMOS of this right circuit? Can see here the B signal is going. B signal is going to the input to the inverter. Now B bar, what will be coming out? B bar will be coming out. B bar will be coming out. And this B bar is going to the input of PMOS and NMOS. Clear? Right? Now what is the gate actually? This gate is nothing but, this gate is nothing but a NOR gate. Right? It's nothing but a NOR gate. So in NOR gate with one input, this guy A dot B whole bar, and another input B bar. So this is something which we need to work on. Okay, so we have a NOR. What are we NORing? A into B bar and B bar we are NORing. So what is NORing? NORing is, this is A into B bar plus B bar whole bar, right? So this is my output. This is my output Z. This is my output Z. A into B bar. So here what we will use? There's a De Morgan law. What is the De Morgan law? You should remember the De Morgan law. What is the De Morgan law? It is A plus B whole bar equal to A bar into B bar. You should remember this simple logical formula or law, Boolean law, right? So if you apply that here, what will get? If you apply that here, we will get A into B, the first input, bar, the bar is splitted, dot B bar whole bar. So what is the peculiarity of this circuit? You can see A into B whole bar. This plus will change into, and bar is splitted, right? That's the only thing we are having. Plus is changed to into, or ORing is changed to ANDing, and the big not gate is splitted into individual bar gates, not gates, right? So this is splitted, and this is changed to ANDing. Again, if we simplify it, what will happen? Again, bar, this two bar can cancel out. So this A bar whole bar is nothing but A bar whole bar is nothing but A. If we double, or if you put a two NOT gates, logical value doesn't change. So then into what? B double bar, again B. So what will got? This is nothing a AND gate. Anyone got any different answer? So I think I just didn't do it completely. So A into B whole bar into, there is something into B, right? So B into B is same logical value, so it's nothing but A into B, right? What is B into B? or we can say B into B, logical value of same as B. Okay, these are the formulas which I used here. So this is nothing but an AND gate. So this thing is AND gate. Okay, so again, uh, I will just tell you how I have came across the answer. So starting, I've seen this two PMOSes connected in parallel and two NMOSes connected in series. So this is a NAND NAND circuit, and this is a NOT circuit, and this is a NOR circuit, right? And my output is my output of my NOT gate, right? And what is NOTing? This is B. B is going to the NOT gate and getting B bar here. Now this B bar is going to the input of one PMOS and one NMOS. And NAND gate output will be, my NAND gate output will be nothing but here A into B whole bar. This is my NAND gate output. This is going to one PMOS and one bottom NMOS, right? So I'm NORing what? The NOR gate has the input A into B bar and B bar, right? So I'm just simplifying that. So I'm just NORing these two things, A into B bar and B bar. So NORing is what? Plus, logically adding and negation. Then I am using the De Morgan's law, that is A plus B whole bar, A plus B whole bar, A plus B whole bar. That is NORing, splitting the bar, A bar into B bar. Okay. So likewise, I changes plus into dot, ORing into ANDing. The bar is splitted. You can see bar is splitted. Okay. So A bar all bar is A only. I know this thing. A bar all bar is A. So this becomes A into B. This becomes A into B and into B double bar again B. So A into B into B. That is nothing but A into B. NAND gate. So this gate is ultimately NAND gate. Okay. Fine. Okay. Now this is another circuit which is given to you. So you can try this circuit. Okay. Here also you can see the pattern. What is the pattern? What is this circuit? This circuit is nothing but a NOT gate, right? This is a NOT gate. And here, if you see here, there is special no special pattern which we have studied. So we have to take it individually, right? So let's see. Okay, I'll give you 2 minutes. You can see if you are able to try this thing. You just need not to confuse here. This two A and B. There's a two path here, A and B, right? And you can say A is going to this PMOS and the top of this PMOS. And you can say B. Let's take B. So B is also going to this PMOS, top of this M2. Okay, I'll give you 2 minutes. You can try this. Find what is the logic. You know, output Y. This is the output. I'm taking from directly from here. Just connected to both things. And this A, you can see A is here. So not gate output is A bar will be here. A bar. And this will be going to the base or input of M4 and uh, source of M3. So you can try. I'll give you some time so that you can try this. This has been shared with you in the Google Classroom. Here you can take some value for A and B and see what are you getting. Okay, let's try. Let's try some
ए
values.
बार आएगा सर इसका ए बार
Output is a bar.
आई थिंक सर
Okay, so a bar. So you can see input is a and b, but output is you're getting a bar.
यस सर
Let's see. Okay, let's take different values. Let's take different values. For example, let's take. Okay, let's take a equal to a and b different values, and let's see what is the output of y. So any other answers? So let's see. Let's we keep both a and b 0. Let's start with 0 0. Right? As usual, our all logical gates start with 0 0. Okay. So here a is 0, b is also 0. You can see both M1 and M2 are on because, right? Why they are on? Because the inputs A and B are going to their control gate, or they are becoming 0 in their input of this PMOSes, right? So they are on. So here I'm getting 0. Here I'm getting 0. So output you can directly see that it is getting output is also 0. Let's confirm there is some more output. So A is 0 here also. So output A bar equal to 1. So this 1 will coming here in the base of this M4 and M4, right? So M4 only, not here. So M4, this is on, this is on. So we know, okay, B is also on the base here given B. So B is also connected to Y. So definitely again the output is high. So circuit is working fine. Again, this A bar is 1 and M3. What is the state of M3? M3 is off. M3 is off because the 0 is going to the base of M3. So it is off. Okay, so output is definitely 0. So 0 0 0. So definitely the answer is not a bar. That is wrong because if it was a bar, then it should be 1. Right? Now let's see the other condition. Now let's put a equal to 1 and b
सर
let it. Yeah.
सर जब ए जीरो था तो
Huh.
एम एम थ्री ऑन होगा ना सर
M3 is NMOS, right?
एम फोर
NMOS.
एम फोर सर एम फोर सर
Uh, NMOS is on. Yeah, NMOS is M3. M4 is
तो
on.
सर
Yeah,
हाई
M4 is on.
तो सर हाई वोल्टेज नहीं लेंगे क्या मतलब वाई में फिर आउटपुट से तो वो भी कनेक्टेड है
No, actually you can see when M4 is on, when
यस सर
M4 is on, you should remember that when M4 is on, what happened? You can see M4 is connecting the B to the Y. You can see? So
ओके सर
M4 is on, so B is actually 0. 0 is connected to Y. Getting?
ओके सर
Here we are taking transistor as a switch. It is just the control signal in the base of M4. That is here. The base of M4 is A is the input of the NOT gate. A bar is the output of the NOT gate. Hence A bar is going to the gate of the M4, and we know A
यस
is 0, so A bar is equal to 1. So M4 is on because it is NMOS. So when M4 is on, its source and drain is connected. That means its end terminals are getting short circuited as well. So B is coming in the output. Getting?
ओके सर थैंक यू सर
So in first condition we got. Now let's see what are the other conditions. Now let's see if we got 0 0 0. That was the initial condition. Now let's make A 1 and B 0. Let's see what is the output here. Now A is 1, B is 0. B is 0 means you can say M1 is on, right? M1 on means the A is coming to the output here. A is coming to the output. That means Y is coming 1, the top from the top. So you may ask if we can decide from directly from the A and B, M1 and M2, then why should we analyze the other part of circuit? Yeah, why I'm analyzing the bottom part of circuit? Because sometimes there may be difference in mismatch in the logical value. Top portion of the circuit will be giving high, bottom portion of the circuit will giving 0 for the Y. So there is a mismatch in the logical values. That means circuit is a wrong, bad circuit. If we have your uh, circuit has a logical value high from the top side, it is charged, bottom side it is, you know, giving 0. That means your circuit is wrong because there is short circuit, because your inputs are getting short circuit. 1 and 0 is getting short circuit, right? So that is why I'm analyzing from both sides, from the top as well as bottom. From the top I'm getting 1, y equal to 1. So let's see a on the bottom part, a equal to 1, so a bar equal to 0. So 0 is coming to this point. Now 0 is going to M4, so M4 is off. Now 0 is also coming to the source of M3. Now let's see what is status of M3. M3 is also off because B is 0. So M3 is also off, right? We can see both M3 and M4 are off in this case. So Y remains 1. So in second case, we know when A is 1 and B is 0, we got output 1. Now let's see if A is 1 and B is also 1, what the change will happen. Okay, so now B is equal to 1. Now this and M1 is also off. M1 is also off, right? M2 is also off, right? So B is 1. So this B will be given 1 to here, and M3 also. So M3 is on, right? So M3 is on, and M3 will be connected. The source of M3 will be connected to the output Y. Now let's see what is value of Y. Now A is 1, so this is 0 only. So 0 is coming from here and is going from here, and um, so I'm just getting confused. So 0 is coming here and 0 is coming to the M4 also, and but here B is 1, right? So your yeah, M3 is high. So this A is 1 and this 0. 0 is connected to the Y here, right? So here I got 0. Am I right? So let's analyze again. Let's analyze again.
1 मिलेगा
Uh,
क्योंकि बी कनेक्ट हुआ सर वाई से
yeah, let's analyze again. Maybe there's some. Okay, let's start from scratch because I was overwriting the things, make it complicated. Okay, now let's start analyzing again. Okay, so A is 1 and B is 1. So both this M1 and M2 are off. That is clear, right? Because base of PMOS is getting, or control terminals or gate of both PMOS M1 and M2 are getting high, so they are off. So you don't need to consider any logical value from the top portion. It doesn't affect the circuit. Now, the whatever logical value your output is going to receive is from the bottom part of circuit. Now let's start assuming analyzing the bottom part of circuit. Now A is 1, so A bar is 0. So the bottom part of circuit is getting 0, right? So 0 is going to the M4 gate. So this is going to be off because NMOS, if a control terminal or gate terminal is 0 voltage, it is off. So M4 is off. Okay. Now this 0 is also going to the source region of M3. Now what is M3 is on or off? It depends on the B. What is B? B is high. So B is high means this one is M3 is on now. So M3 is on because B is high. So this 0 is going to the Y. So Y becomes 0. Okay. So one thing is both M1 and M2 are off because A and B are high. So both PMOSes at the top is off. We don't need to consider that. Now we're considering bottom. A is 1. So NOT gate. This is nothing but A bar. A bar is nothing but 0. So 0 is making the M4 also off. M4 also off. Okay. And but B is high. So B is making M3 on. M3 on. So B makes A bar go into the Y. Right? So very simple. So Y becomes 0. Clear?
यस सर
Okay. So you just need some patience. That's it. You need patience and you need to check each individual cases. Right. So this field of, if you understand, this field is a digital VLSI design or VLSI design, where as a circuit designer, electronics engineers, VLSI engineers are designing different kinds of gates, chips or even processor part. Basically, you know, all the microprocessor, any RAM or digital things is basically comprised of different types of individual gates, not gate, and gate, or gate. You know, the what are the fundamental gates you can see, which is NAND gate and NOR gate, right? And NOT gate. So because using NAND gate and NOR gate, you can make all other gates. But using AND gate and OR gate, you may not be able to make other gates like XOR gate, XNOR gate, NAND gate, NOR gate. But using NAND gate and NOR gate, I can make all of them. So usually they are called universal gates, right? So basic, all this, if you know to make NAND gate and NOR gate, you can make all the processors, all the memory, everything. Okay, so that is part of digital design, and advanced design is part of digital VLSI. Okay, so let's now analyze the last condition. Let's analyze the last condition. So I'll again rub those things so that we can analyze last condition. So what is remaining now? Last condition remaining is 0 1. 0 1 condition is remaining. Okay, so 0, A is 0 and B is 1. Let's see what will be the output value. So A is 0, B is 1. So definitely M1 will be off because B is 1. But M2 will be on because A is 0. So B is directly going to the output from the top. That means Y equal to 1 because B is 1 and M2 is on. Okay. Now let's see what the bottom. On the bottom circuit, what logical value we are getting. Okay. So A is 0. So A is 0. A is 0. So A bar equal to 1. A bar equal to 1 for the bottom circuit. So this 1 is going to the M4. M4. So M4 is also on. M4 is also on. Right. And this 1 is also going to source of M3. Now what is B? B is 1. You can see B is 1 here. So this one B is high. This high value of B is also short circuited to Y. So Y again we can ensure that Y is high not only from bottom but also top. Right. So it is strengthened. Right. And M3 is also on. M3 is also on. Again it is strengthened by this one from the A bar. Okay. So we got one. So what type of gate is this? We have the fourth condition completed. So what kind of gate is this? 0 0 0 1 0 1 1 1 0 0 1 1.
XOR gate.
Yeah, this is definitely XOR gate. Fine. So although, for example, if you know this is a perfect design, this can be much easily analyzed. You just focus on the top. You can see this is these two things A and B. Already you have this A and B, and just knowing this part of circuit, just analyzing the top part of circuit, you can understand this what is the output value. You need not consider the bottom part, right? Because here in this case you're assuming the circuit is perfect, workingly perfect. There's no error in the circuit. You just need to find the logical value, right? Because you don't expect any different logical value coming from the downside because it's designed by someone, uh, a good designer. No error can be expected. So if we think like this, say from different condition we can see from here A is 0, B is 0. We know both transistors are on, so output is definitely 0. So 0 0 0. Now what about 1 1? 1 1 we can say both transistors off. M1 is off, M2 is off. So bottom part we may be giving maybe some other value. Maybe say this is 1, A is 1, so output is 0. So 0 is coming and making M4 on, and B is 1, so this is 1. So you can see, oh, B is 1 0. Okay, so M4 is off. M4 is off, right? And this is getting 0. What about M3? M3 is also on, and so 0 output is 0. Okay, 1 1 we got this 0. Okay. Why I analyze here the bottom circuit? Because both of these PMOSs are off. So I just went to the bottom part of it. Okay. Now 1 and 0, in 1 and 0 we know the B is 0, so M1 is on, so output is 1, right? So, and reverse also. Reverse also, if 1 and 0, M2 is on, M1 is off. So definitely output is 1, right? So just analyzing the top part of the circuit, we can conclude that working also. Right. Okay, so although it looks a bit lengthy, but just need I just want you to know how the different circuits are. I'm not telling you to design anything. I'm just telling you to understand what is this circuit is doing, the functionality of the circuit. So that's all for today. I think if any doubts you can ask.